started, my name is Eric Young, for those of you who don't know me. The speaker today is Svirsky, who's an associate professor of otolaryngology at Indiana University. Dr. Svirsky did his undergraduate work in Uruguay and came to Tulane for a PhD in biomedical engineering, and then went to MIT where he worked in the speech lab with Joe Perkel. And slowly and gradually drifted from speech production to cochlear implants, and today, and now he's at Indiana University in a group with Rich Miyamoto and others working on cochlear implants, and so the work he's going to tell us about today is entitled Multidimensional Phoneme Identification, a new framework to investigate speech perception by cochlear implant users.
Thank you. It's a pleasure to be here. Thanks for the invitation. It was a lot of fun to chat with many of you throughout the day. First, let me start by acknowledging some of my colleagues and the various organizations that have given us money. So I'm going to start by telling you the good news about cochlear implants. As most of you may know, cochlear implants are neural prostheses, artificial devices, to help the profoundly deaf or severely deaf hear. Cochlear implants allow most users to communicate orally, face-to-face in a fluent fashion. Many cochlear implant users, I would say most at this point, can also communicate without visual cues, so they can have a telephone conversation, even if it's somewhat limited sometimes. Over the years, since the beginning of cochlear implants, there has been substantial progress in the clinical results and in our basic understanding. By progress in clinical results, what I mean is that the typical patient who used the first models of multi-channel cochlear implants may have been able to understand 1 word out of 10 if that word was presented sound alone and the patient had no other cues to identify it. These days it's more like 4 words out of 10. But the bad news is that many cochlear implant users obtain limited benefit. That rough average that I told you of 40% single word identification is an average that's composed of people who get over 90% and a few who get 5 or 0%. Another problem is that this progress that I told you about has happened mostly in a trial and error fashion. That's because our knowledge of the mechanisms of speech perception by CI users, cochlear implant users, is also somewhat limited. So this aspect of my research program has as a long-term goal to explain how cochlear implant users understand speech. I'm trying to explain how they encode, combine, and represent acoustic cues and how they employ these cues to perform lexical access. This is a long-term goal, but not the specific aim in my grant, which has to be limited to something that you can achieve reasonably within 5 years. So the short-term goal is to develop a model of phoneme identification. So I'm just talking about identification of individual speech sounds, either vowels or consonants. This model is based on an individual's psychophysical ability to discriminate along relevant acoustic dimensions. And there are 2 reasons why I want to do this. One of them is that the study of speech perception by CI users may provide insights about speech perception in general by people with normal hearing. In that case, you could say, well, why not study normal hearing people then? Well, I think this is a very interesting population to study because they receive much less information about speech than normal hearing people. And that gives us a chance to model that process in somewhat more detail than we would be able to in the case of normal hearing people. The other motivation is clinical. if we know more about how cochlear implants work and the brains of the patients who use them, how they work, this knowledge may help guide the search for improved cochlear implants. I thought you would get a kick out of this. I don't think it's absolutely necessary for this audience, but in the field of audiology and speech and hearing, as you know, there aren't too many people using computational approaches. So frequently I feel the need to justify myself in front of my audiology colleagues. So the example I use is this. Suppose an extraterrestrial came to Earth and wanted to know how cars work, okay? By observing the phenomenon from the outside, they might be able to conclude that when you press on the gas, the car accelerates more. And maybe even see that there's a different pedal that you can use to brake and so on. And you could construct very detailed functions relating displacement of the pedals to the car's acceleration. But that wouldn't tell you anything about how the internal combustion engine works. And that's the kind of thing that we try to do with a computational approach to speech perception. So today's presentation is going to have 4 parts. First, I'm going to describe the guts of the model that I'm using. Then I'm going to talk about 2 applications of that model. The first one will be modeling of vowel identification by cochlear implant users. This will be restricted to English speakers. And the second application that I'm going to talk about is point number 3 here. We're going to use the model to get a quantitative measure of adaptation to speech perception with a shifted frequency map. And finally, we'll conclude with some overall conclusions and future work. Let's start then with a description of the MPI model. This is based on signal detection theory. And those of you who know Breda and Derlach's model of intensity discrimination published,
Yeah, I'm sorry, I don't know basically anything about cochlear implants.
Okay.
And who the target set of patients who use them are. Could you say a little bit about each of them?
Yeah, I have some information about cochlear implants later on, but let me give you the capsule right now.
Okay.
The typical patient who receives a cochlear implant is a person who's profoundly deaf and who gets limited or no benefit from hearing aids. These are people with sensory neural deafness. That means that hair cells, the neurons that perform acoustic to electrical transduction, basically do not work. So amplifying the sound does not work because it won't be transduced into a signal that can be sent to the brain. So what cochlear implants do is to stimulate spiral ganglion cells in the auditory nerve directly with electrical impulses. These devices have many electrodes, as you will see later, and with each electrode we can stimulate a slightly different population of neurons. So if you stimulate electrode 1, you get a certain pitch. With electrode 2, you get a somewhat different pitch, and so on.
So are the patients deaf from birth then?
And this is used by either postlingually deafened adults, people who became deaf later in life, or by people who are congenitally deaf and who are implanted relatively early on. Some people who are congenitally deaf, profoundly deaf, and who have received cochlear implants later in life have not done so well. Okay? So let me show you another slide to give you an idea of one stimulation strategy, what one specific cochlear implant does with the signal. Okay, the speech signal is subdivided. They take the speech range, which is which has variable meanings depending on the context, and that's subdivided into frequency bands. That spectrum is analyzed on a short-term basis once every few milliseconds, say from 0.5 to 4 milliseconds. And the average spectrum over that period, you get the amplitude, the amount of energy within each frequency band. With the speak strategy, which is the one I'm going to talk about first, the algorithm looks for the channels that have more energy. In this case, we see 6 channels that are highlighted in orange. And those channels with more energy determine the electrodes inside the cochlea that will be stimulated. So in this cycle, these 6 electrodes will be stimulated. What you see here is a model of the rolled out cochlea with electrodes in it, and each electrode is associated with a frequency band on a one-to-one basis. Okay, so this is kind of like a vocoder approach, except you're only using some channels, not all of them.
This is binary.
I'm sorry?
The electrodes are binary.
The electrodes are, well, you use 2 rings inside the cochlea to form a channel.
No, the signal is straight down the electrode.
Oh, the signal that you send to the electrode. The signal that's sent to the electrode is a pulse, and the amplitude, actually the energy of that pulse is monotonic with the amount of energy found within the corresponding acoustic band. In the case of the speak strategy, each stimulation cycle is repeated at a rate of about 250 hertz, once every 4 milliseconds. So let me go back to the model now and describe its general characteristics. Some of my slides have a lot of graphic stuff, so the computer is slow going from one to the next. So basically this model is an extension of Breda and Derlach's intensity model to many dimensions. We hypothesize that all the dimensions are orthogonal and that the space is Euclidean. The bottom line of the model in terms of input-output is that it attempts to predict phoneme identification based on discrimination performance along relevant perceptual dimensions. So the inputs to the model are J and Ds, just noticeable differences along different acoustic dimensions, and the output is a confusion matrix, either a vowel confusion matrix or a consonant confusion matrix. I'll show you an example of that later on. Some of the concepts that we use are the following. A phoneme, that is a vowel or a consonant, is identified based on acoustic cues, which may assume different values for each phoneme along the respective perceptual dimension. Now, one important characteristic of the model is that due to limitations in auditory processing and in memory, percepts in response to the same physical stimulus vary stochastically. Okay? For example, if you take a vowel, and if we say that the relevant dimensions are the first and second formant, then the Gaussian distribution associated with that vowel has a center that's determined by the physical characteristics of the phoneme, that is the first and the second formant. And the spread of each Gaussian distribution is determined by the subject's discrimination. So you can think of what this model does really is associate each speech sound with, if you imagine a 3-dimensional perceptual space, it's like a fuzzy ball in space, okay? The center of that ball, yep?
No.
Oh, okay. The center of that ball is determined by the physical characteristics of the stimulus, and the spread of the fuzzy ball is dependent on the subject's ability to discriminate along each one of the dimensions. What I'm showing here is a 2-dimensional example, where, for example, use this instead. This could be formant 1, this could be formant 2. The idea is that a listener with a a good listener with relatively good discrimination and therefore a small, just noticeable difference along each one of the two dimensions, whenever you present the word hod, you would have a percept that varies within this region, which is relatively constrained. As you can see in this example, different vowels have their own little regions that do not overlap. This is an example of an average listener with a somewhat worse JND. Because of that, the center of each distribution is the same as in the other example, but the spread is much more. So in this case, there's some overlap between distributions, and that overlap is what determines the confusions that the model predicts the patient will make. So by first picking the dimensions that you think are relevant, finding the characteristics of the stimuli, and changing the JND, you end up with very different confusion matrices. Let me illustrate that with an example. This is what a confusion matrix looks like. The idea is that in this kind of test, you present vowels, for example, the H vowel D context, head, head, hood, many times to a patient, and the patient has to tell you which vowel he or she heard. So you compile all the responses. For example, if the stimulus is had and the response is hod, you would put that response in this cell here. Okay. In this example, what I'm doing is taking some outputs of the MPI model, assuming that the dimensions are F1, F2, and F3, and this slider changes the J and D, the just noticeable difference. If I move it all the way to the left, that's a patient with very good discrimination, which results in a confusion matrix that's pretty darn good, because as you can see, most responses fall in the diagonal, so the percent correct is very high. As the J and D's change to worse and worse numbers, you see that more confusions start to occur, and until we get to a really bad J and D. Now the correct responses are fewer than in the original case. And we can also see that that some vowel pairs are confused, others are not. What the MPI model attempts to do is to match the patterns of confusions, the matrices that actually are obtained behaviorally from cochlear implant patients. Presumably, if you pick the right dimensions, you could obtain a good match. For those of you who prefer block diagrams, this is an example of the MPI model in 3 dimensions. So for English vowels, the data I'm going to present to you will assume that the relevant dimensions are the average value of F1, F2, and F3, the first 3 formats of speech. So what the model does is the stimulus goes through 3 information extractors for F1, F2, and F3. You can compute this. And that information is corrupted by noise. This noise represents imperfections in the patient's sensory capabilities or memory representations, short-term memory. So because of this noise, we end up with an estimate of the stimulus along the F1, F2, and F3 dimension that's subject to some stochastic variation. All right? So that Gaussian distribution that I showed you is equivalent in here to what we see at the outputs of this estimation process. So we have a percept that varies stochastically along each one of the 3 dimensions. This percept is compared to the best exemplars of possible responses. Subjects know they have stored in long-term memory representations of each speech sound. For example, E should have a certain F1, F2, and F3. That's stored over here, as well as the exemplars for A, U, and all the other vowels. So this percept is compared to all the exemplars, and the closest exemplar is the patient's response. Okay, so the mechanism, one of the mechanisms by which errors happen is if we have a lot of noise here, then the estimates of F1, F2, and F3 will be more corrupted, and therefore this percept can be far away enough from the correct exemplar that the subject makes an error. So in summary, to implement a version of the MPI model, what we need to do is first to hypothesize what dimensions are relevant to the specific phenomenon that we want to model. Then we need to measure each stimulus along each one of these dimensions. Then estimate or measure J and D to plug that into the model. And finally, we have a fourth step that's optional, we don't always use it, which is to estimate or measure perceptual bias. Let me explain briefly the concept of perceptual bias. And these are the graphs with a lot of information, so it may take a while. Okay. So this is again an imaginary two-dimensional model where the two dimensions are this one and this one. And these are three speech tokens. Let's call them apa, aba, and ama. And this is the hypothetical perceptual space of a patient who has good discrimination. We know that because these distributions don't overlap too much. With that kind of discrimination, the patient could potentially perform 100% at identifying these three sounds. However, in order to do that, he has to have the right partition of the perceptual space. Okay? By partition, I mean that this perceptual space, which is part of a plane, needs to be subdivided into response regions, so that if a percept falls in the red region, the patient will respond apa. If it falls in the green region, he will respond ama, and so on. So this is a good partition of the perceptual space, one with no bias. Let me show you now an example of a perceptual space that's similar, but with a different decision criterion. Okay? In this case, the red region corresponds to the apa sound. As you can see, in this case, for this patient, there will be many examples of aba and ama that will fall in the red region. And therefore, this subject will make errors, not because he confuses the different sounds, but because he assigns the wrong labels to them. Okay, so this is what I mean by bias. Okay, and what I would like to do now is to present to you two examples of application of the MPI model. In the first one, we will assume that there is no bias, no response bias in the patients, and the results will be quite good. In the second example will be that we'll see that we have to assume a non-zero bias. Otherwise, you can't explain the results that happen. Before we move on to that, let me show you one comparison method that I use to compare observed matrices to the matrices predicted by the model. This matrix was observed in a patient whose initials are not NEN. Oh yeah, I remember why. NEN is the Spanish acronym for doesn't hear a thing. This is a patient with very low performance. So I remember who she is. And this is the actual confusion matrix. You can see that the numbers are quite low. I mean, it's above chance, but barely. Okay, this is one predicted matrix that was obtained with the model. And there are many ways in which you compare this matrix to the previous one. One thing I do is to look at a certain threshold, say 10%, and determine what vowel pairs are confused more than 10% of the time or less than 10% of the time. For example, look at heard and had. Heard 10%. had 11. So on average, had and heard are confused 10.5% of the time. That's the average of 10 and 11. Other vowel pairs are not confused more than 10% of the time. For example, had and head are confused an average of 7% of the time, the average of 10 and 4. So what we do is go through the two matrices and look at all the vowel pairs that the model predicts will be confused more than 10% of the time, and that actually are confused more than 10% of the time. Those are indicated in green here. Okay, the white numbers are the vowel pairs that the model predicts will be confused less than 10% of the time, and actually are confused less than 10% of the time. So green and white are cases where the model successfully predicts something. In blue, I have indicated a case where the model predicts confusions more than 10% of the time, 14.5. But if you look at the actual data, the confusions are only 7% of the time, which is less than 10. So that's a failure of the model. And finally,
just out of curiosity, I'm trying to make sense of the perceptual bias thing, and I noticed that you have some vowels left out. Is that just an accident? That ah is not there, for example, what's the competition for ah? I'm trying to make sense of what's here and what's not, and why they, I was trying to look for asymmetrical competitive positions, and I went to law because law I would consider to be a social perceptual bias, and then I couldn't find ah, and I went with.
Yeah, the reason why we only have one such phoneme here is because of this test that I used, that's widely used in this population, the Iowa vowel test. It only has these 9 vowels. So there was no theoretical reason for including or excluding. I guess one theoretical reason would be that the first data sets that I have are from patients at MIT, and many of our patients there don't have an ah distinction in their.
In that case, they'll lack all.
I don't know what would happen in their confusion. Some of them will probably be confused. I can tell you that in terms of producing it, they produce the same sound when they are prompted by written versions of.
Okay, well, I guess I'm going to remain confused as long as I don't understand. Are the stimuli naturally spoken?
Yes.
Okay.
But
the cones that you were showing as targets, those were perceptual, not related to the actual productions. Actual stimuli.
Well, when we run the model, each separate production, each separate example of, for example, the word head, is measured separately, because there's some variability in speech production, obviously. So we take that into account by modeling responses to each stimulus using the experiment. But I suggest that we wait until the second part of the talk to look at bias, because the first data set that I'll show you, I didn't really find any, and all I'm trying to do with these matrices is to show you the one way I summarize the confusions. And basically the kind of summary that I end up with looks like this. It's a 2x2 matrix where we find that in the real data, the subject confuses, in this example, 13 vowel pairs, and 11 of those are predicted by the model. 2 of those were not predicted by the models, so these are misses. And this is the number of false positives, vowel pairs that the model predicts will be confused, but are not confused. Ideally, if the model worked well, we would like to see numbers in these 2 cells, but zeros in here. At the very least, we would like to see that the model predicts most of the errors that are made. In other words, this number is greater than this one, with few false positives.
What would this look like for normal?
The vowel confusion matrices for a normal human person, they would be perfect. I mean, this test is very easy for you and me. Okay, so let's move on to one example. We're going to model some vowel identification, vowel confusion matrices obtained from cochlear implant users. Well, I don't need to tell you that in English, the values of the first three phonemic frequencies are very important to identify vowels. They are not the only cues, but they are probably the most important ones. And we have known this since 1952 when Peterson and Barney measured the frequencies of spectra from vowels obtained from men, women, and children, and found that most of these vowels occupy distinct regions in the F1, F2 plane. For example, E occupies this region with little overlap with others. And before we actually apply the model, let me describe the speak strategy in some more detail. As I said before, this is basically a 20-channel vocoder where each channel in the vocoder is mapped to one electrode. On average, 6 channels are stimulated each cycle, and the cycles are repeated 250 times per second. Importantly, there are different ways to map acoustic frequency to electrodes. So in this example that I showed you, they used all the range up to 10 kilohertz, but you could just as easily use a smaller range, and that's actually done. This is just to give you a feel for what that strategy ends up doing. This is a spectrograph of the word choice with the CH here, the OI diphthong over here, and the frication noise for the S up here. Can you see the pointer when I move it? Yeah, it's hard to see. But anyway, the CA, this is an electrodograph. So this axis is time, just like in a spectrograph. This axis shows electrode, and electrodes are mapped to frequency. So you can think of the y-axis as frequency as well. And just like in a spectrograph, the color encodes intensity of stimulation. And here you can see that the CH is well represented. You see the diphthong for the OI, that's the second formant, and the third one here. And finally the frication noise for the S. So as I said before, there are different frequency to electrode tables that can be programmed by clinicians. Those frequency to electrode tables result in different stimulation patterns and, more importantly, in different vowel identification scores. Margot Skinner, in a landmark study of 2 such frequency to electrode tables, found that table 9, which was the default for use in patients with cochlear implants with a nucleus device, obtained about 78% vowel identification with that table. However, using another table, table 7, their vowel identification was significantly higher. So let me show you those 2 tables, and let's look at the differences for a little bit. The original table 9 maps the frequency range up to 11 kilohertz or so, whereas table 7 uses a more restricted frequency range up to 8.7 kilohertz or so. So we're getting rid of some information from 8.7 kilohertz to 11 kilohertz, but it's information that doesn't have that much speech content. On the other hand, we are assigning smaller frequency bands to each electrode. These are smaller than these, and therefore we may be providing more ability to discriminate frequency. If you look at the F1 range, that's encoded by 5 electrodes here, 5 point something electrodes with table 7, and only 4 electrodes in table 9. So it makes sense intuitively that people should understand vowels better with table 7 than table 9. So we attempted to model the experiment that Margot Skinner did. What she did was to conduct a 10 vowel identification experiment with 7 subjects. Each vowel was repeated 6 times in the medial context for each table, and the tables 7 and 9 were tested in an AB-AB fashion, meaning that first table 7 for half the subjects, or 9 for the other half, then the other table, and they were switched 2 more times. There were 3 weeks of experience with each table, so subject could adapt to the new frequency to electrode table before testing was done. The motivation, what we try to accomplish with these studies, to determine why do CI users understand vowels better with table 7 than with table 9, see if we could explain why they confuse some vowel pairs but not others, and finally speculate whether some other table may be even better than the one Margot Skinner used. So to apply the MPI model, first we need to pick the dimensions. In this case, as I said before, we know that F1, F2, and F3 are important. So what we did was to obtain electrodograms of different vowels. This is E in this example, with table 9 and with table 7. This is the F1 energy here as a function of time. We took the 100 milliseconds in the middle of the vowel. And this histogram shows the accumulated pulses throughout the 100 milliseconds weighted by the amplitude. And finally, we found the center of gravity for the F1, F2, and F3 region, which are shown with arrows here. And as you can see, these arrows are located in slightly different places for table 9 than for table 7. This means that within our framework, the vowel E is in a slightly different position in perceptual space than for table 7. So the third step and the fourth step would be to find the JMDs and the bias. In terms of JMDs, instead of measuring them, we estimate them because we didn't have access to those subjects. So in this case, the JMD for form and frequency discrimination was a free parameter. And finally, we assumed that response bias was 0. To illustrate the well, you know what we mean by a free parameter. Basically, we generated predicted matrices for different values of JMD, and then we adjusted this slider to find the value of JMD that would give us the best fits to the data. So this is the observed data, the average for all the subjects that Margot Skinner tested, and this is the best fit we could obtain with a model assuming F1, F2, and F3 as dimensions. This is the comparison of the two matrices in terms of error pattern. And we looked at vowel pairs that were confused more than 1% of the time. So what this tells us is that this very simple model with just 1 degree of freedom was able to predict 7 out of the 10 vowel pairs that were confused by the subjects. And that 7 of the 11 predictions made by the model were borne out by the data. Also that the model was able to predict 31 out of the 35 pairs that were not confused by the subject. Interestingly, when we plug the same value of JMD in the model using table 7 and table 9, we find about the same difference, the same advantage for table 7 as was found in the actual data. Okay? And this is obtained with no degrees of freedom actually, because we plug the same JMD into the model. Perhaps the most interesting thing that you can do with a model like this is see what would happen with other frequency to electrode tables. If you remember, table 9 used the frequency range up to 11 kilohertz, table 7 used a range only up to a more limited number. And as you go lower in that number, it's a more and more restricted frequency range. Now, if Margot Skinner wanted to repeat her experiment with all available frequency tables and sent a proposal to NIH to do that, she would not get funded because it would take too much time and money to do all that. Now, she's an excellent clinician and has an excellent sense for what might work, and that's the reason why she tested table 7. But if you want to test all possible variations of stimulation strategies, that's just not doable. And that's one domain where a computational model like this can be exceedingly useful as a guide for things you may want to try with patients. what we found was that we conducted simulations for different values of J and D, and we found that for values that we may find in patients from 0.3 to 1.5, this is the J and D in terms of interelectrode distances. So this will be a patient who can tell the difference between stimulation that's delivered to one place or to another place that's 1.5 electrodes apart in terms of distance in the cochlea. This will be about 1 millimeter of distance in the cochlea. So we see that as we go to lower and lower number maps, patients, the predicted performance will be better, but it kind of saturates at about map 7. So you can't really do a heck of a lot better than that, at least according to the model. In fact, Bob Shannon tested a few patients with map 1, which patients hated, and not only did they not get any better than with map 7, they actually got worse. And the reason why they got worse, a bit worse than the model would predict, has to do with perceptual bias, and that's what we will talk about in the second part of the presentation. So to summarize this part, a simple model of vowel perception with only one free parameter correctly predicts the superiority of one frequency to electrode table over another, and most of the specific vowel pairs that will or will not be confused by CI users. And I think it's a very remarkable result given the simplicity of the model. I should tell you that we tried subsets of the 3 dimensions that we used, F1, F2, and F3, and the fit is not nearly as good as when we use all 3 dimensions. This is in English. In Spanish it's different. You don't need F3 in Spanish. Yes?
So you just had one JMD that was for all of the different forms, is that correct? And independent of what frequency they were at?
Yes, the JMD measured in millimeters of distance along the cochlea. I assumed, for simplification purposes, that it would be the same. Now we know that that's not really true in real patients, because there can be local differences in the F1, F2, and F3 regions. However, we have no evidence of systematic differences. So to model individual patients, this was probably an oversimplification, but to model a group of patients, it was probably okay. So given that the results were decent, I think it's, it justifies that simplification to some extent.
The audio data which you use with the patient for the actual test,
yes.
How variable is it in the sense that it have only one speaker or does it have multiple
The audio data that we use is the Iowa test of vowel perception, which uses one speaker, and it uses 3 repetitions of each one of those 9 vowels.
Okay.
So it's single speaker, there's some variability, and not a lot.
And do you by any chance have any audio examples that you could play?
I'd rather move on to the second part of the talk, but I do have examples that I need to look for in my hard disk, and I can play them for you later. You're going to have to listen to them through the tinny speaker, but it should give you some information. So let me move on to another study. Vowel perception, well, neural plasticity is kind of an overstatement, but adaptation or learning in cochlear implant users. The effect of more basal than normal stimulation. What do I mean by this? Well, as you guys know, as well as I do, the cochlea is tonotopic. So if you take a cochlea and roll it out and feed pure tone to it, if the pure tone has a very low frequency, the place of maximum stimulation will be closer to the apex. As the frequency gets higher, the stimulation moves to the base. Here I have plotted the second format of 3 vowels, those in the words hid, hud, and had. And as you can see, those second formats, spoken by a female probably, stimulate different places of the cochlea. in a normal hearing person. When someone receives the cochlear implants, here we have the same rolled out cochlea. We have a bunch of electrodes which are represented in black. Okay? But those electrodes, for surgical reasons, don't extend all the way to the apex of the cochlea. Okay? So we end up with a situation where the most apical electrode may be in the region that corresponds to perhaps 1000 hertz or even higher. So because of the way we encode stimulation in the cochlear implant, the word HOD has a second format with 800 hertz that may correspond to this electrode, and therefore we're stimulating the place that corresponds to HID in a normal cochlea. So in other words, these patients receive maximum stimulation from the second format here in response to the word HID, but now they receive stimulation shifted more to the base in response to the same word. That's what I mean by more basal than normal stimulation. Now, is that a problem? And as I do this and I hear the sound of the overheads, I remember Peter Jusik because he always used to use overheads all the time as opposed to slides, which is my common in the group of people I hang out with. But anyway, I was saying, is that a problem? And let me set up two hypotheses about the plasticity of the place code. And these hypotheses are not strong, and they have been articulated by people in the cochlear implant field to different extents. The physiological correctness hypothesis would state that natural stimulation is crucial, and therefore pulses that encode formants should be sent to the physiologically correct place in the cochlea. That is, to the place that received maximal stimulation in a normal hearing listener. The research I will tell you about was done with people who had hearing before, lost it, and then received the cochlear implant. So their memories of sounds could be different from what we send them. The other hypothesis is the all you need is contrast. Basically, it doesn't matter what place you stimulate. As long as you provide contrast, patients will adapt because the brain is a wonderful thing and it's plastic and it will deal with stuff. Okay? So the study had two goals. First, to discover mechanisms of vowel perception with cochlear implants, and two, to perform a quantitative test of these two hypotheses about plasticity of the place code. The physiological correctness hypothesis and the all you need is contrast hypothesis. The speech perception data that we used were some vowel confusion matrices, this time obtained using synthetic vowel stimuli, done by Peter Blamey at the University of Melbourne. He used 50 presentations for each one of 6 vowels. He tested 4 subjects who were long-term users of the F0, F2 stimulation strategy with the nucleus 22 cochlear implants. This strategy is not used anymore in a clinical setting, but it's very interesting, and I will tell you why. It's interesting because it stimulates only one place in the cochlea for every stimulation cycle, and that place is selected based on the value of the second format. So instead of stimulating many places in response to many formats, there's only one place. And this illustrates the strategy. These are spectra obtained as a function of time. So this axis is time, this one is frequency, and the z-axis is amplitude. What the processing does is to find the value of the second formant and then stimulate one electrode based on that value. Okay? So because different vowels have different second formants, they will tend to stimulate different parts of the cochlea. To apply the MPI model.
Doesn't it also provide F1 information?
No, there was another strategy that superseded this one that was called F0, F1, F2 that stimulated 2 places in the cochlea. This strategy is older and only uses F2. And because of that, it's only one place. The patient does not have access to any interformant distances, only the absolute location of one formant. So we assume that the relevant dimension in this case would be the place of stimulation in response to the F2 of the stimulus. Step 2 is to measure the stimuli, and those values are described in the original Phoneme and Clark paper. Finding the J and Ds for place of stimulation in the cochlea was done in another study out of Australia, in which I collaborated with Peter Blaney, and this was based on a pitch scaling procedure. So we obtained estimated D primes and J and Ds from that. Finally, in this case, response bias was a free parameter. The amount of bias that optimized the model's fit to the data was obtained. And I will show you how that was done. First, let me show you the actual data from one of the subjects. This is a confusion matrix for the 6 vowels, and these vowels are ordered by decreasing second formant. So as you can see, most of the errors happen to the left side of the diagonal. Okay, that's the bias I'm talking about. So that's because subjects confuse vowels for other vowels that have a higher second formant. That's a bias that's consistent with the more basal than normal location of the electrodes. If I say that because if things are shifted in the fashion I described several overheads ago, then what you would predict is that when you present, say, hard, subjects would confuse that for a vowel that has a much higher second formant. And that seems to happen to some extent.
Is this a subject that's been using the implant for a long time?
Yes, all 4 subjects in this study had used the implant for at least 1 year, in some cases much more than a year.
Does it matter how long they had normal hearing before did they have it through, let's say, age 5, 6?
Well, with 4 subjects, I can't tell.
Okay. It wasn't early, it wasn't at like...
Oh no, this was late, definitely. So the top graph shows the real data again. The bottom graph shows the prediction made by the MPI model, assuming that the physiological correctness hypothesis is true, and that the response centers that the patient has, the places where he expects to be stimulated in response to each vowel, are the same places that were stimulated when he or she had normal hearing. Because of that, that patient will be predicted to make a lot of errors, and all the responses are shifted to the left. And percent correct would be only 17%. Clearly that did not happen. So this is a really bad prediction.
So this is based on this subject's actual electrode position in the cochlea?
On the actual electrode position in the cochlea, yes, and on the subject's J and Ds as well. Now this shows the predicted performance if the patient's response centers, or the expectations as to how vowels should sound, are a perfect match to what we're actually sending. So this is no bias, and it's what will be predicted by the all you need is contrast hypothesis. That hypothesis over-predicts what the subject did. You see that there's 61% correctness to the 46, and we don't see the bias in the responses. We have about equal numbers of errors in both sides of the diagonal. So what we did was to shift the response centers, the patient's expectations, from the actual place of stimulation, and look at the difference between the predicted and observed matrix. So as we shift those response centers, as illustrated down here, this is what happens. This is the RMS difference between 2 matrices. We see that we reach a minimum at about 0.5, 0.6 millimeters of shift in the cochlea. This is the distance between response centers and stimulation places that provides the best fit to the data. And let me show you that fit obtained for a bias of 0.53 millimeters. As you can see, if you go through the different cells, you know, the match is not perfect, but it is pretty good. In particular, all the vowel pairs that are confused more than 10% of the time are perfectly predicted by the model in the case of this subject, as indicated by the summary matrix up here. And these are the results that we obtained for the other 3 subjects. So as you can see, the model did quite well in terms of predicting vowels that would be confused or not confused by users of the F0, F2 stimulation strategy. So in terms of the first goal, a simple model based on channel discrimination, which was measured, and perceptual bias, which was the only free parameter of the model, could explain vowel perception by 4 individual users of the F0, F2 stimulation strategy. But this is what I think is the most interesting part of the talk. The most interesting slide. It requires some explanation. What we see here are results for 4 patients. Okay, so let's take this patient, 67. This axis shows place in terms of millimeters from the cochlear apex. Okay, this is the apex, this is the base, so numbers go up this way. These purple circles indicate the place of electrical stimulation in response to each one of the 6 vowels that were used in the experiment. Okay? These red triangles are estimates of the places that were maximally stimulated when the subjects had normal hearing. We are assuming that Greenwood's equation is relevant here and that the subjects had average size cochlea of 35 millimeters of length. And finally, the green squares are the response centers that maximize the model's fit to the data. If the subjects were behaving according to the physiological correctness hypothesis, the response centers, their expectations, should be superimposed with the places of natural stimulation. And on the other hand, if they were behaving according to the all-you-need-is contrast hypothesis, the green squares should be lined up with the places that we actually stimulate, showing perfect adaptation to that stimulation. And we see that in all 4 cases, the green squares are closer to the place of electrical stimulation than to the place of natural stimulation, but not quite. There's a residual bias that remains in all 4 patients. We measure the average bias for all 4 patients and what we call the basal shift. The shift is the distance between places stimulated when the subject had normal hearing and places stimulated with a cochlear implant. So that's the shift that we impose with a cochlear implant. The bias is the fraction of that shift that patients were not able to overcome, which is the distance between their current expectations, indicated by the green response centers, and the places that are actually stimulated. When we look at the basal shift and bias for all 4 patients, we find that the basal shift is different for all of them. That's because the electrodes were not inserted all the way, completely all the way in all 4 patients. So some of them had a more shallow insertion because you couldn't force the electrodes all the way in. And in that case, you have a greater basal shift, a few more millimeters than these subjects. This is the part of the basal shift that each subject was unable to overcome, indicated in millimeters in the cochlea, and this is the ratio of average bias with respect to the initial basal shift. So this first column means that subject P07 received a shift in his stimulation of 5.16 millimeters, and he was able to overcome 90% of that, but not the last 10%.
What is the JMD for each of
the
I mean, I just wonder if there's a correlation between J&D and bias.
Well, with 4 data points, I can't, I wouldn't speculate unless it was so huge that it would hit you over the head, but it doesn't. I don't remember what the G&Ds were off the top of my head, but I do remember that there was not a clear relation between the J&D and the bias. And there was no relation between the basal shift and the bias either. As you can see, these subjects had a really poor insertion, but this guy was able to overcome most of it, whereas this guy had a much more complete insertion of the electrodes, and yet he or she was unable to overcome a relatively big chunk of it. So this is related to a conversation we're having over lunch about the possible relation between electrode location and speech perception. It's probably important, but it's affected by the subject's ability to adapt to a shift.
The question here it's kind of related to what was asked a minute ago, is how far do you really have to shift in order to get some basal level of speech perception? So if the subject's J&D is this much, there's no point in shifting much more than here, because it's probably a lot of work to shift. And
Right.
if you can get all the speech, in other words, it doesn't make any difference where you end up in this range for your speech perception. They might not bother to.
Right. This model predicts that vowel identification should be a function of both J&D and bias. And those are two very different reasons why a subject may be unable to perform at top level. J&D probably doesn't change too much over time, but I think that bias can be overcome to a large extent. In fact, that's what we find in patients with newer devices that encode many different formats, like the speak strategy. In those patients, we find no evidence of bias when we measure it directly using a method of adjustment procedure. So to conclude, in terms of testing these two hypotheses, we find that to a large extent, CI users do adapt to more basically normal stimulation, but some people adapt more completely than others. When there is residual bias, it's always in the direction of normal stimulation. So at least with this strategy, which is kind of a worst case, but nonetheless, with the F0 F2 strategy, listener responses fall in between the Ovididis contrast and the physiological correctness hypothesis, but fortunately closer to the former than to the PC hypothesis. My hypothesis is that when patients first receive electrical stimulation, their response centers correspond to the places that were stimulated when they had normal hearing. So they expect kind of the same thing. After implantation, patients adjust the response centers towards the places actually stimulated by the implant. To test this hypothesis, we are embarked in a project where we're measuring this kind of performance, both J&Ds and speech perception, longitudinally in several patients. We do this starting the day of initial stimulation, before the patients have heard any speech through the implant, so they haven't had the chance to adapt at all. We are also imaging the cochleas of these patients to obtain actual measures of the length of their cochleas and electrode location. Actually, Darlene Ketten is doing that using her method. So that way we'll have much better estimates of perceptual bias. So to conclude, we only saw a few examples of application of the model, basically vowel perception in English for the speak strategy, group data, but we have used the model successfully to explain several results. The first publication coming out of that is in JASA in March of 2000. In terms of future work, I just described some of it. Other things we propose to do is to collect data from individual users, both experienced and new, refining the model, possibly adding more dimensions or changing it from a model where all dimensions are the same, to another one where dimensions are considered in a sequential fashion, hierarchical fashion, and extending this work to both children with cochlear implants and to open set word recognition rather than recognition of individual phonemes. And it's our hope that this kind of work and the insights that we result from it will help the development of new stimulation strategies and will allow us to fit patients in a more informed basis than it's currently done in clinical practice. And that's basically it. Thank you very much.
I had a question about the chart where you had the purple, green, and red.
Okay.
The thing was with patient 16, the one who had the closest insertion into the cochlea. I was wondering whether the fact that it's so close to the natural point of stimulation is why the patient is having a hard time adjusting. In the sense that
Patient 16.
right. So if you compare 16 with 36, most of the stimulus that the patient receives from the implant is so different from the natural points that, in other words,
For patient 36, it's very different from the natural point.
that there is in other words, if I received the implant and I had to adapt my own perception, it's easy because I'm hearing something I never heard before, and in some sense it's clear how I have to adapt. What I'm wondering is whether for patient 16, 3 of the 6 vowels are in the region where I normally would see stimulation.
So he would say this is close enough, no reason to adapt?
No, it's not clear what it is because it sounds like something else that I know. In other words, of course I'm extrapolating based on one point, which is always a dangerous thing to do. So, but I'm wondering whether that's a factor because I just noticed that that's the patient whose adaptation is the poorest.
Well, my account of that would be that that's the patient where adaptation is the poorest because he's the least plastic one. And, he's the one who had the best shot at having no bias whatsoever because there was less basal shift to begin with. I guess it would be interesting to test whether these same patients have different abilities to adapt to other kinds of novel signals in cognitively based tests. I don't know.
Yeah, because what I'm thinking is this is coupled with the question about the JNV, the range over which the patient is unable to distinguish things. And this already starts putting a lot of the examples, let's say the lowest vowel, many of the purple one, many of the stimulus would probably be a little below that because there is some variation in the stimulus also. And if that starts overlapping with the region for the green triangle corresponding to that vowel, then you would perhaps not want to adjust because it kind of sounds like what it would be anyway. And in other words, there's an inhibition to adapt because some of the stimulus almost falls into what it would sound like. When the patient had no, I'm just speculating, but is there more data that you haven't shown us which says this is not the case? That there are patients with pretty much perfect insertions who do adapt to whatever remains?
No, this is basically it. I'm not going to get any more data because there are no patients programmed with this strategy anymore. What we find in patients who use the speak strategy, which encodes many formats, I have tested them after 1 year of use of the device, and what we found in that case is that there was no bias. The task was, we used a method of adjustment task, where you have a screen in 2 dimensions, and when you click on different parts of the screen, you hear vowels that vary in F1 and F2. So the patient sees a vowel on top of the screen like E, and he's instructed to select the region that sounds like E. Okay? If there was a bias, then patients would select regions that are systematically shifted from those selected by normal hearing people. And we found no evidence of a systematic shift. Some patients with poor JNVs selected huge regions for each vowel. Patients with good speech perception and small JNDs selected more constrained regions that were indistinguishable from normally hearing people. But again, we found no evidence of any systematic shift. This is in JASA this year.
And for a normal person, how many millimeters is the JND? Is it half a millimeter, even less?
Oh, I would say less than half a millimeter.
It's about 50 hertz generally for second form.
50 hertz or less than 1%.
Okay, so in other words,
It's going to be very small.
okay, it's very small. On the y-axis over here, it's barely noticeable.
Much less than half a millimeter.
Okay.
Yes.
Two questions. Do you have any patients who are bilingual and who did both the 5-vowel and 10-vowel type response?
I only tested one patient like that once.
Is there any anomalies, or is everything pretty much the same?
Well, she wasn't really bilingual. She was a very good English speaker, and
For something as simple as these tests, a person who has a 5-vowel system and takes the test, it ought to be interesting to see how much prediction you get from the model against the Spanish versus English on the same individual.
right. My recollection from those data is that the prediction obtained in her native language of Spanish was quite good, but in English there were some errors that couldn't be explained simply based on a poor J&D. In other words, she confused some non-native contrasts more than you would expect. But that's what happens to normally hearing people as well. So that's a reasonable result from that point. For example, confusing heed and hid more than you would expect from an English-speaking cochlear implant user.
How good a predictor is performance on this set of clinical tests for actual performance of speech in a fluent environment? Real speech perception skill.
In other words, if we measure the JNDs for the dimensions that we think are important,
Yes.
to what extent that predicts performance in more realistic speech tests?
Well, see, I guess what is bothering me is that this is a neat test based on discrimination. But of course, the real problem in speech is the space is always full, and the problem is to identify what's there. You know, the examples of E that you're going to hear, the examples of A that you're going to hear in real speech are
very
not well
different.
behaved.
Yes.
And the real trick is to just decide which one it is and get on with it. So I wonder how well predicted real speech perception behavior is from this test.
That's an excellent question, and that would be, kind of my long-term goal. As I said at the beginning, I think that's a very ambitious one, but not one that I could reasonably attempt to complete within 5 years. And you're absolutely right. The errors that I can predict are those, that happen in reasonably well-behaved vowels, always within the same context by a single speaker.
Sure, I mean, a vowel like "ugh" hardly ever occurs. You never get it, and it's still, you can go all day long without ever hearing "ugh," and do perfectly fine. So it's a good measure to take in a clinical test, but it's not necessarily going to enter into.
Well, but there are systematic relations between performance in these vowel and consonant tests and more realistic tests like single word identification or sentence identification. In fact, for example, if you take a patient, conduct a vowel identification, consonant identification, and single word identification in open set, what we have found in our population is that the multiple R for a linear model is like 0.99. So it's highly predictive in a way, if you will. But only predictive in the sense that the linear model fits quite well, which is not a lot to say. And there are systematic relations between single word identification and understanding speech in sentences.
Well, since the hour is getting a little late, why don't we stop here? I'm sure Dr. Svirsky would be happy to answer more questions if anybody wants to discuss things with even more detail. Thank you.